Okay, yeah. So this week we are going to be essentially reviewing a handful of concepts that we expect to be talking about and in greater detail and building upon next week during Focus Week. So why don't we just go ahead and go in order of the discussion that we had on Monday in terms of responsibility. So that's going to start off with Ramy, if that's cool with you, Ramy. Kick it off with a conversation on columns and behavior.
Yeah. Uh, yeah, my review is pretty basic because I think we already still remember all of this.
Yeah, and maybe for your context, Jeff, and anyone else who wasn't at the Monday meeting, we're trying to do like fairly quick overviews, so like 15 minutes maybe to describe it, and then 15 minutes of discussion. But we'll see if that's realistic. And then I think if we end up overrunning, we could always start part of the focus week with covering any of these topics that we think are particularly important. But yeah.
Okay. Yeah, so this is a behavioral columns recap, but as always, we like to start with the morphology learning uh, column as well, which we already have discussed. But there's one detail that I want to add to the end of the morphology column, so this is why I thought I'd start from the beginning. When we're learning morphology, we assume that we have all the time that we need to learn the morphology in a fixed state, right? It's not moving or anything. So we start looking at we're basically just learning features at locations, and we're building this reference frame. We're building a model of the object bit by bit. So we basically start moving from one location to another. We're moving in the reference frame and the locations in the reference frame layer 6, and we're looking at different features here, and we're just storing those based on where we see these features. So we end up seeing different features, and then we're just building this bit by bit, like I said, and we keep doing this until we end up with a model of the object. This model is usually just stored in layer 2, 3 as an object ID. So could be just like a random SDR that is associated with those features at locations. Now the next part is something that we've discussed more recently. I don't know if this was in the original idea of how we're learning morphologies, but it's mostly about how we can learn every object ID so that we're actually learning states or keyframes, and we can learn transitions between them in a like you learning a temporal memory, like in HTM we can learn like higher order sequence. So if we see the object in a different state and we also have a lot of time, we can build another keyframe, and then we can also learn it in exactly the same way until we learn that keyframe, and then we store it also in layer 2, 3. But the interesting bit is that we can learn the higher order sequence similar to so this is the temporal dimension in the morphology column, similar to how we're learning the temporal dimension in behavior, but it's being learned in a different way in the behavior. But here it's being learned as transitions between object states. Does this make sense, or is this part?
What's TM? Sorry, I think I missed
Temporal
it.
memory.
So this is the new idea that I haven't heard before. So just state that. Is that correct?
It's written in our documentations that in the object behavior documentation that we can have that the morphology column can learn states between
Right.
can learn transitions between states as I
Right.
see.
That it would learn different key state frames, but it wasn't that the idea that we learn the transition between those states in the morphology column is something that I haven't heard before. Is that something? Am I correct about that? Or?
Well, I think we talked about that every column has the exact same mechanisms. So if the behavior column can learn transitions between states, the morphology column technically has that ability too. So Input, you could learn that.
Yeah.
Yeah, and
Like
would
if you
also get
learn
the time input.
it wouldn't really usually be like continuous behaviors, but more like the switch between the red light and the green light or something where you have two
Okay, right.
morphologies that you
So
switch
this
between.
example of the stapler would be probably not really possible because you have all these in between transitions which are modeled in the behavioral model.
Yeah,
And you wouldn't really, but if I had like a green light turning to a red light, yes, I see that could potentially be done here.
Hmm.
but you
Or if
could
you have like two consecutive keyframes, and you just like stop at the next keyframe, you may be able to learn like transition
Well,
between those
well,
keyframes.
but it takes time to learn the keyframes, right? So it's not like you instantly know this. I'd have to learn these different states some other previous time. So I
yeah, I
couldn't
mean,
learn it.
I would say you could learn like some states of the stapler, like the stapler can be open or closed, and you have a representation of how the stapler looks in these two states, but then you wouldn't learn like a detailed representation of all of the states in between.
You wouldn't learn how it went between those. So you
Yeah,
couldn't
Right.
learn the transition. You couldn't learn this transition as we think about the stapler opening and closing.
yeah.
Yeah.
That wouldn't be, so that's a bit misleading to say, oh yeah, we can learn all this stuff here as well. No, that learning the stapler opening closing would require behavior models.
Right. But if we have already learned these object states from in the past, and we're just inferring these, so if we're inferring the state closed, and then after 1 second we're inferring it that it's opened, can we learn a temporal memory?
I don't know. Maybe, but I wouldn't assume that's what's
I,
going on.
yeah,
Because you can be going both ways. You could see the stapler at different points in time, open and close, and it's not always going to be transitioning. So it's a bit muddy.
yeah. I mean, I think I see what you're saying, Jeff, and like like how long it would take to go between these. And it's not like that's something that's consistent, and certainly
Where
not instantaneous.
right,
Whereas with something like the traffic light, it's a
right.
bit more. But yeah, I
I
think if nothing else, I think we agree that we would have these different keyframes. The
right,
question is whether you would learn kind of some sort of sequence here. Kind of depends on how they tend to manifest in the world.
right, right,
But
right.
I
That's
think
correct.
what's probably more likely with something like a stapler is maybe like one keyframe is kind of associated, or like these two keyframes are associated with a behavior model, and maybe what state we're in that behavior model tells us kind of what state to expect in the morphology model or something like that. So like
Right, right,
they
right.
kind of bounce back and forth. So it's like the closed stapler kind of is associated with the beginning in the behavioral model of the hinge,
Right.
and then
This gets back to when we learned causality. That was done more here, right? Where you could say, oh, the particular state of this object would invoke a particular behavior in another object or something like that, or another state in another object, but as opposed to learning how the stapler opens and closes. I think we can all agree that like there would be different morphology states for something like a stapler or a switch. So I agree with all that. I think we have to. It's the issue of whether we're
and also
learning.
that sequence memory could take place
It could, but
in
I
layers,
could,
but yeah, it
but
would only be
I
under certain
I
conditions. And
I think it's. I don't. I'm not even sure. It could, but I wouldn't go under that hypothesis right now because as soon as something starts to move, then you invoke a different model. It's not the same model anymore. It's a behavioral model. Um, and the morphology model is, I just wouldn't make that assumption. This
Yeah, maybe
could,
with like a traffic light or something where the morphology isn't, there's no movement, but there's a change in the state of the object
right.
that's timed.
So we can say for certain that if this mechanism existed like this, it wouldn't be sufficient to learn the behaviors of objects. It might
Mm.
double or tack on to some other stuff, but the general learning behaviors of objects requires behavioral models, and this can't suffice. So we don't want to mislead ourselves thinking, oh, this can happen here too. I don't think it can. It might be learning these transitions. It might say, oh, I want to see the stapler open. It's going to be closed in 2 seconds. It's possible. But the general behavior of a stapler is not going to be learned here.
Yeah, and even if it's learned here, it wouldn't actually be a behavior because we cannot really apply it to other objects. It would just be
Right,
specific to
right,
this.
right. So I
need
would have,
changes.
I would have taken this temporal memory thing and say, you know, oh wait, this is an interesting idea. Maybe it would happen. I don't know, but let's leave it out for the moment.
Right. Yeah. Um, okay. So that was morphology. Behavior takes a similar route. It's just that the only difference here is that we're storing changes at locations. We're not storing features anymore. So and there's a difference in the way that these are learned, because in the behavior everything is moving. So you have to take into consideration the temporal dimension. It's not like you're learning the state first and then you're transitioning from one state to another. Like you basically have to fill in information at different time steps in the memory of the object, in the memory of the behavior. So it would look something like this. Right now we're just trying to learn the behavior of its the stapler opening, not closing. So it's just from state 1 to state 2, and it would look something like this. It's moving. We are moving at the same time that the sensor is moving and the object is moving, and we're basically storing a different change in basically like a different state over here. And then we now have to rewatch the behavior so that we can fill in more of the details of that behavior. And this is one of the obstacles that we talked about before, why we would need shared learning and things like that, is that when we were just observing that first part here, we don't know what's happening in the rest of the object. Because as we move from time step 1 to time step 2, all of that information is basically lost because it's in the previous time step. So we'd have to rewatch that behavior. And let's say we're sampling from a different location here now, and then do this again, and we start filling in these missing information in the model of the behavior. Yeah, and then after a while, you basically build that behavior, which consists of multiple states over time. And I don't know if we've agreed on this or not, but if we would have temporal memory between those states, this is also a part that's unclear to
No,
me.
I don't think it's necessary here at all.
Okay.
I'm not sure why we would do that.
Yeah, I think the Scott is going to talk about the time cell mechanism that we could use for learning the temporal, like the intervals between transitioning from state to state and when to expect the next state.
Yeah. Okay, cool.
But yeah, didn't that use kind of a combination, like as in a state predicts another state subject to a certain amount of time passing?
Well,
So whether we want to call that temporal memory or not, I don't know if,
well,
yeah.
I wouldn't do it in the layer 2, 3. That doesn't make sense. I think it's in layer 4. These are details maybe we don't want to go into right now. But I think we're glossing over some of the details we have gone into in the past about what's exactly going on in layer 4 and what's going on in layers 2, 3 that are important here. So where this transitions are occurring, I think this simple diagram leaves a lot of open questions about it. We also talked about, in learning the behavioral models, we talked about how in the staple example, we thought that the way you described Ramy is like you're looking at the whole system through a straw, and but we talked earlier about how when the stapler would open, you would probably attend to the top half as a whole, and so you'd see that you'd break that as a sort of a separate object in a child region, and that whole object was be rotated. Remember that?
Yeah.
So we wouldn't necessarily be learning every point like this. We would be the learning problem would be a bit more subtle and less onerous. I'm just throwing in something. This is not a complete description of what we've talked about in the past.
Yeah. But also when we were talking about actions, I remember from previous discussions that we split these into states, into like behavior states, and we started thinking about how we can move, like what action do we need to represent so that we can move from one state to another, and we had those as different states. And I'm not sure if we brought up temporal memory as a way of learning that sequence, but Yeah, I could be wrong here.
Yeah, yeah. I think part of the problem was as we thought about the stapler more and other examples, we realized that, if you say, what is the equivalent of the temporal pooling operation in layer 3? Remember, layer 2, 3 in our morphology model is essentially you pool, or you associate a whole series of feature location to a particular SDR, and so that would be the ID for that object. Here, what was the equivalent for behavioral state? Well, then we started thinking about it. It's like, well, it's not stapler. It could be like the top of the stapler is going up is one thing, and the top of the stapler is going down is another thing. So there isn't, I think we got to the point of thinking about the layers 2, 3, like what is the equivalent of the temporal pooling over the stapler. So there was some subtlety there as well, which we talked about. I don't remember all of it right
Yeah.
now.
So, but yeah, that brings me to the next point where if there's temporal pooling here, then is it possible that we're also doing like second order pooling on top of these sequences of states, as in?
Well, it's possible. We've talked about that in general. Right. We talked about it in lots of different ways. We talked about doing that, for example, in morphology models to get classes. But those are just ideas we threw out. I don't think we've ever just flushed them out or convinced ourselves they're real. So if you want to talk about that now, that's all right.
Well, this is a recap, so I shouldn't really bring up more like new ideas, but I just want to throw this out there. If we were thinking about these as learning like a more specific behavior, which is incorrect because we said this would not be an actual behavior. And this one, if we're sorry, go ahead.
Oh, so left is the morphology model and right is
The
the
left is,
behavior.
sorry.
Yeah. Okay. Right.
Yeah, I think
Uh,
it would be the left would just be stapler, and that would be the object ID, and the object can be in different states. And then, yeah, the right is the opening behavior.
So the object ID here would be just a stapler. I was thinking if we have temporal memory that learns the transitions as a higher order sequence, if we pull over that, then we would have the stapler opening, which is a more specific representation of the of the stapler actually going from one state to another.
Yeah,
Yeah,
but
but
we can have that in the behavior column as the I mean, the stapler itself can go through various ways. You can halfway open it and close it again, and you can go the opposite direction. And so for like learning morphology model of all of these possible transitions would be too expensive for every object. So we just want that in the behavior model, and then the morphology
Yeah.
model can have different morphological states of that object, but we don't necessarily need to learn all of the
Yeah.
possible transitions of these states.
right.
And this was my attempt to, so this would be a many-to-one associative connection here. Like different objects are basically using the same generic behavior that can apply to different objects. And I was thinking of associative connections here as a way of applying a behavior to like learning the mapping between a generic behavior and how it would apply to the specific object. But again, this is all new speculations and probably incorrect.
Right. It's not really review at this point.
Yeah.
So
Yeah, and
this
like
is
I think on the right hand, I think it's an open question whether we would need higher order pooling like shown here, or kind of like Jeff is saying, like with compositionality and what representation we'd have coming in. Like you could imagine L4 is representing the kind of bar of the stapler coming up, and then the pooling there for the opening is happening in L2, L3.
Yeah.
But yeah.
I'm not sure I got
So-
that part. You mean you'd pull over the features being common, or what do you mean?
Over the over the changes happening in L4.
But in the morphology model, we don't have changes.
Yeah, I'm not talking about in the morphology model.
Oh, you're talking about pulling in the behavior model?
The behavior one, yeah.
Okay.
Like just kind of shifting all of that down, basically.
I missed all that, but
Yeah, I'm not sure it's helpful to spend too much time on it. I guess it's just that
Yeah, I think generally the blue arrows, arrow swarms, whatever, they would be in layer 4 and layer 6, and then layer 2, 3 would just be like a state representation of all of like a pooled state representation of them.
yeah,
Right.
that's what I was saying.
Over
Right.
space and time. And this is the bit that confuses me a little bit because here we're pulling over space and time. Here we're just pulling over space. And I was trying to
Well, it's
make a bit more
no,
sense.
well, no, it's space and time because the sensor's moving, right? You don't get all those features at once. So on the left side, the morphology model, the time is by the sensor moving through time. And on the right, you've both got this potentially we have the objects moving and the sensor may be also be moving. So they're both pulling over space and time.
And
That's why
and
it's
yeah,
Well,
I guess with the
that's
morphology one, it can be in different states at different points in time. It's just that being in a particular state doesn't predict transitioning to another one in the same way that it does in the behavioral model.
right,
So
right,
you still kind of pull over time in that sense. It's just
right.
Yeah, but you
yeah,
don't have to like the features are consistent at the same spatial location. The feature will always be consistent here. So you can take away that time dimension because the object is not moving.
No,
Uh,
but the sensor's moving. So what layer 4 is representing is changing, right?
but the
It's just
reference
there's
frame doesn't really have a time dimension.
no, but there is time. So this comment came up in the concept of temporal pooling. You're pooling over time and space in the temporal pooler in layer 2, 3, and you're pulling over time and space, both of those, right? Because one case, the time, because your sensor is moving through time, this because the object's moving and the sensor may be moving. I was just referring to the comment
Yeah,
you said where the temporal pooling, you said only is over time on the right, but not over time on the left. But no, it's both cases. You're pooling a bunch of SDRs that occur over time, and that's why it's called temporal pooling because you're
yeah,
pooling over time on both of them. The object may not be moving, but the sensor's moving. It takes time to sense the object.
yeah. I guess I'm more referring to like the representation that's being learned doesn't really have a temporal dimension that we pull over. We just
Right, but
but
the
it
beauty
can
of
do. I mean, that information is coming into L1, so it's kind of up to the column whether that information is useful. And it just
yeah,
happens to be the case that with most morphology models,
so let
it's not really necessary.
so the beauty of this, and I think Vivian really caught on it early, was that we should be able to use virtually the exact same mechanism for these two models. Really, the only difference is that the nature of the feature. The feature in one case is representing something static, and the feature in the other place is something that has changed. It's not, it doesn't, all it says is this point on the object has changed. That's all it is. And everything else should work the same. That should be our working assumption. So I think when I hear this conversation, many of the confusions come about because we're abandoning that basic premise and or we've forgotten it or something like that. So really, there should be really almost no difference between these two models, other than one is getting features that are representing a change at some point in the object, and the others are getting features that represent a static thing at one point in the object. But beyond that, they're pretty much the same. So we have to
yeah,
keep that in mind as we go through this. And we may have to deviate from that. We may find out that's not really true, but that should be our working assumption all along, that they're exactly the same, and see where it doesn't work.
yeah.
Right. So I'm not sure how this relates into what we're doing next week yet. So I'm not sure.
It's just a series of reviews just to figure
But
out
it's
what's right.
but do we have a topic for next week where this is background for that? Is that the
Well,
idea?
yeah, we thought, I mean, it would be good that all of us understand behavior models because they are important for figuring out which actions to take. So
Uh,
if we talk about how do we turn a light switch on or how do we push the stapler
okay.
down, we need to know how the behavior models work.
Okay.
So
Well, we didn't get very far before we had found a lot of things we didn't understand that were agreed upon. So, well, it's
yeah,
good
and
we're
that's
doing it.
what the session should be about, that
Right.
we make sure everyone
Okay.
agrees on the same kind of foundational concepts.
Okay.
And
Okay.
yeah, we have the
Right.
same basis.
Right. Well, maybe.
But yeah, I mean, I don't know if your concern, Ramy, is that we kind of have time available in the morphology model, but it feels like it's not being used. Is that one way of
No,
paraphrasing?
the description you said about how the time is available through layer one and it's just not being used. That makes sense because we wouldn't need to use it if the object is not moving. So basically the reference frame would collapse along the time dimension.
Or yeah, or at least it's not like predictive. It's not like
Yeah, it doesn't. Yeah,
in something like a stapler. But there would be, yeah, there might be kind of morphology type models, kind of keyframes where it's like, oh, I see this one and now I expect to be in this other one.
yeah.
Yeah, I
But
think that's true. I think you could learn. I mean, if you talk about it that way, if the different keyframes occurred at some regular intervals, um, then you could just ask, well, would it learn those transitions? It probably would, right? It could learn that, hey, this keyframe ID goes to this keyframe ID after a second. If that information is available, the column, it could learn that. I'm not sure what to do with that in terms of the overall system here, but we can again file that in the back of our heads, like, oh yeah, a morphology model could potentially learn the order of keyframes or could learn, the timing of keyframes. But again, I think that's more relevant if the keyframes change suddenly, like the light type of thing. I'm not sure if it applies generally.
yeah,
Yeah,
That
thanks.
puts us at
Are
about
there
the
any
half
other
hour
kind of
mark.
open?
Yeah.
Oh, sorry.
Oh, sorry. I was going to say that puts us at about the half hour mark, and it seems like a natural
Okay, nice.
closure and
Yeah.
opening up to the
Yeah, I
next.
guess if there's anything else that's unclear on behaviors, it's worth bringing up now. If anyone has any.
There's a lot. There's a lot of stuff.
I mean, obviously there's a lot, yeah, we still need to solve, but
I
yeah,
mean,
maybe we can
maybe
come back to that.
Scott's presentation will go into those topics
That's
more
true.
now with the time representation.
Right.
So,
Right.
Right.
Yeah,
I think
sounds good.
the only missing part that I didn't bring up is how we can represent compositional, like the morphology can be part of the behavior in a higher level, and then the behavior can also be part of a morphology. But I think we understand that, or I didn't have time to put slides for those, so
Yeah, we can always revisit that later if we need
yeah, I
to.
mean, just at a high level, I guess the idea is that it would use the same mechanism as we use for compositional objects, only that behavior IDs can also become feature inputs to higher level columns. And the movement of object, like the change in object location and orientation, could also be change input to a behavior column. So yeah, basically using the existing mechanisms we already have
yeah.
to.
Right. But we've never walked through a complete example of that. At least I don't remember. Um, it sounds good, but I don't know if we really worked out all the details.
Yeah, I mean, for example, if you recognize the spinning behavior on the wheel of a car, you have the behavior ID of spinning. That would be the
Right.
output of the column. And then that could become feature input to the column that's modeling the car,
Right.
and it would
Right.
associate that behavior to the car model.
Right. Maybe
And
I'm saying we haven't implemented this yet, so we don't know what the problems are going to be.
yeah,
Right.
and I guess I'm saying I don't like once our compositionality work is done in Monty, if we add behaviors, we wouldn't need to implement any addition to
Right.
Monty
Right.
because we
Right.
already have the ability to model compositional objects, and
Right.
behavior IDs are just treated the same as
Right.
object IDs.
Okay. I'm just guessing that we'll run into some issues and we implement it and say, oh, we didn't think of that. We didn't think of that.
Yeah, like there
My,
might be some of the top-down stuff where it's, not just predicting location, but also state and stuff like
I
that.
don't know what it is. All right. I think we have a good understanding from a pure theory point of view about that.
So I'll just I think this will be pretty short, but just as a quick
Don't say
overview
that.
here. I just had to jinx it. Um, so just as a brief recap, we've got this idea that matrix cells of the thalamus are sending a global timing signal out to cortex. And when I say global timing signal, the way we've got this sort of laid out in the docs and the theory is that we're really talking about like a delay since some last event, time since last event. And what exactly event means is obviously important. and how that's specified. But we're going to sort of leave that alone for the moment. But the basic idea is that this timing signal, it arrives in L1 and synapses onto L3 and L5 dendrites. Um, and so here's one question, I guess, which is timing signals set off a cascade of time cells, which I'm not
So
actually clear on whether or not they're in the thalamus or whether they're local to the cortex.
okay. If it's a cascade, it's in. We're talking about the thalamus.
Okay.
Yeah, I was thinking of it as being in the thalamus,
Okay. All right.
because those are kind of shared.
The
Okay.
cells that they're marking, right? The cells that are marking time are shared across the whole cortex, or at least some modality, just as Neil said.
All right. I
So
just wanted to be super
you can
clear about
imagine
that.
I think we saw a paper like that where they had a bunch of cells and you could see them activating in sequence. Those in this theory are in the matrix. Those are the matrix cells.
Yeah,
Okay.
I think that may have been in hippocampus or cortex, but I also think it'll be one of those things where if you look in cortex, you might see a cell that kind of looks like one of these because it's receiving an input from these matrix cells and or something like that. But
Yeah, that
but
makes
yeah,
sense.
and it, I guess to your next point about kind of it making altering the signal, that way these time cells can be modulated kind of by everyone, and everyone
Mhm.
kind of gets that change.
Right. Right. So, as Niels just said, and in the next two bullet points, um, signals back to the thalamus can alter the rate of this global timing signal so that, uh, let's say, in an example of a melody or something, where somebody is playing back a melody that you've heard before, and it seems to be coming at a slower rate than you expected or a faster rate than you expected. You can send back a signal to the thalamus and say, "Hey, speed up your timing signal or slow down your timing signal in order to match what in order to be consistent with what I'm observing here and recognizing." So yeah, this is just
We
straight from
don't,
our
by the way,
doc.
we don't we don't have a specific theory about how what's that signal back looks like, or how it's implemented. It doesn't matter. We know that this has to occur. So this is an observation that this does occur. So we can just we know that there's a shared timing signal because all the different columns are going to use the same signal. That one part of the auditory cortex is not working at a different speed to the other part of the auditory cortex, and then that they all need to speed up and slow down at the same time, which requires a centralized source for both the timing signal and the speeding up and slowing down.
Yeah.
So we
That
don't
just
need to know exactly where it is.
right. Yeah, like if it's via L5 projections or but
Right.
yeah, that just reminded me of not a totally serious example, but how I think there's studies that when people are driving, if they're listening to like high BPM music, they start driving faster and kind of more erratically. But their
Is that
entire
true?
I think but I think we could make different cases for why that happens,
I
but
mean,
I
it's
think
true when you're running, right? Like, I mean, often, when you go to a gym, like trying to listen to, I mean, I don't know
yeah,
if
I
it's
mean,
just
it
in my
could
mind.
like that could involve the amygdala and all kinds like it could be quite messy why that happens. But I think it's just funny to think about how like you know at least at a perceptual level, yeah, the importance of this kind of synchronization. I mean, I think it makes sense from a point of view of like voting that that everyone needs to agree and stuff like that. So
It's interesting if I think about this theory of the matrix cells. Um, One of the things I read about the matrix cells when I said, "Hey, I wonder if this could be the global timing signal," is that they project broadly within a modality, and so that's the word, but that we use. So, like one set of matrix cells would project over all the visual regions, and another set of matrix cells would project over all the auditory regions. So I always just assumed, oh, well, that means that I can keep a separate beat you know, like when I'm driving the car, I wouldn't speed up when I'm listening to fast music, right? That would imply that. I'm just pointing out that that observation, this idea that they're separate modalities, came from the observation that someone wrote that the physically don't project across modalities. But it was just, you know, it was one observation that I read one place. So I guess it's a somewhat open question about, we shouldn't take it as gospel that the matrix cells don't project more broadly. Maybe they do. You know, you wrote here global, and I said, oh, I'm thinking, oh, it's not really global, it's modality, global and modality, but we don't really know, I guess I should say. So I'm just pointing out that my bias towards modality specific came from that observation about anatomy, which may not be 100% true.
Okay.
Who knows? But it did feel like I should be able to. I always felt like, oh, I should be able to sing a tune while I'm, you know, uh, doing some sort of driving exercise, and they shouldn't impact one another. But maybe that's not true. I don't know.
I mean, it definitely
All right.
seems like at least the reset signal for the timer can be across modalities. Like, for example, when you're listening to a melody and you're tapping your foot to it to kind of count in
Right,
the breaks,
right,
you
right,
don't hear your foot tapping, but you can use it to know like when the next beat should be expected.
right. I think a good thing for Monty is, Monty, we're not going to be singing tunes and driving cars for a while, so we can just assume it's global and for the moment, and see what happens. For a lot of applications, that'll be
Yeah,
true.
Niels and I actually just talked with one external person who's interested in implementing the global timer. And that was one of the
Really?
questions. Should we make it like just truly global, or should we allow for several timers that can be connected to different learning modules?
Well, if I was writing code for this, I would write separate learning modules that be connected to different sensory modalities. So I think Niels just said a moment ago, if columns are voting together on something, then they would probably want to share timing. It could be dynamic. It could be, these signals are available, and you might say when the brain is born, you come out, these signals are broadcast everywhere, the voting signals and the timing signals. And through learning in the real world, we pare back the ones that aren't useful. Something, a philosophy like
Right.
that would make
Or
sense.
yeah, one thing I was thinking about earlier today was just it feels kind of interesting how the global, or maybe partially global nature of the timing signal feels kind of analogous to the global um, attention focusing. And
Right.
yeah, just whether I don't know, just the way what you were saying just now, like whether there's almost like different time signals that you can tune into. Um,
Mm.
so maybe there are multiple kind of going along, but maybe you'd kind of focus on one or something.
I think it's
Um,
pretty clear. It's pretty clear you wouldn't have a separate time signal for each column. That just doesn't make any sense.
sure,
The columns that are modeling the same thing have to share the same time signal.
but
Um,
like kind of to the example that Vivian gave, like maybe when you're listening to a song, that's the kind of one that you focus on, and so that almost like becomes
right,
available to motor cortex.
right, right, right.
But
But
it would be hard to focus on multiple at once. But maybe some amount of kind of attention free behaviors could make use of these ones that are happening in parallel that aren't the center of attention. Again,
right, all right,
driving while doing
right,
something. So like
right, right.
it's just kind of like the space how you kind of have one main focus of attention, but that doesn't mean all of the columns shut down. And
Right,
maybe something similar for time.
right. Well, look, yeah. So this idea that you can attend to one thing, most of the brain is attending, and that's the hippocampus, and that's whatever, and then some other parts can still be doing some rote stuff. Right,
Yeah, but
right,
yeah, I think that's a good point, Niels, that it doesn't seem like you can do two at a time actively. Like you can't tap your foot in a totally different rhythm from a song that you're singing. Like unless the tapping is like a fraction of the rhythm of the song you're singing,
yeah, right,
I
right,
think it's
right, right.
extremely difficult. You'd kind of have to learn the
Right. But I feel like I could like run really fast while singing a song slowly, maybe. But that's only because I feel like when I'm running fast, that's going to be kind of a background process that's not requiring
Well,
attention
but
or
running
something like
instant
that.
because
Where
running
singing a song slower than I normally would, like that's going to require kind of a focus of
so
attention.
running is largely a subcortical process. So imagine you're running along on a level path and you're just running, and you're singing a song, whatever. But all of a sudden there's some things in the path that you have to decide how to get around this, or this, don't step on the dog poo or whatever it is. And I think then you're gonna stop singing. It's it's like if I'm having a conversation in the car and then something happens in the road and that I have to figure out how to handle, I stop talking about the conversation. I just stop, I can't do that. I'm focusing on the road now, All right. I don't think these are really important questions at this point in time. I think the idea that there is a signal that is shared among columns that are modeling same objects. And from the neuroscience point of view, yes, this is we think this is the matrix cells and going to layer 1. From a Monty point of view, that doesn't really matter. And I think the nature of this time is important because it's not a global clock, it's a shot clock or a countdown clock type of thing. Or not even a countdown clock, it's a count up clock with a limit.
Yeah, I mean, I guess, just to the point that Niels brought up with only keeping track of one time at a time, that for Monty, that could be relevant in the sense that we could just have one global timer. And then if you focus your attention to something else, that'll get a different speed. And if you shift it to something else, it'll get a different speed. So
Right.
We wouldn't necessarily have to have separate timers for different modalities that keep track there in each of the modalities at different speeds.
Yeah.
Right. I think that'd be the right approach to start with. We can always change
Yeah,
it later if
that's
we had to.
kind of
I was thinking
that's kind
about
of what we wanted to do.
right. I was thinking about the music in the car thing again. It's interesting. Often I'm listening to music, and of course, if I'm listening to music, it's going to continue, right? So it's like it doesn't feel like I've stopped. But if I'm actually singing a song at some elevated speed, I'm not sure. And then I have to do something else that requires attention. I'm not sure I can continue doing that. I think I might have to stop singing. Anyway, it's just more observations. All right, so we agree that we can just start with one global clock, right? That's what
Okay.
you said.
Oh,
That's what you just said, Vivian, I think. I think that's what you just
Yeah.
said.
Yeah.
All right. So this is just a figure in the docs. I think everything in here has been stated, but just depicting that there's some sort of timer signal that's being relayed to the learning modules in addition to sensory information. So this is another example from the docs. So what's being depicted here is essentially this is our sort of clock. And I think, Vivian, you can feel free to chime in here, but these are meant to represent essentially different layer 1 activations. Is this correct? In this clock here?
Yeah, I mean, you could think of it as either the matrix cells or the input to layer 1. Yeah.
The input to layer 1. It's not the layer 1 cells
Yeah.
themselves.
Yeah, exactly. It
Right.
would be the input to layer 1.
That
So
these cells, these are the time cells, so they're in the matrix.
yeah.
Yes. Okay, yeah. And essentially what's going to happen is what's considered an event here is a note. And so we're gonna, each note here lasts essentially like 2 clicks. We get a new event. And each time we sort of reset to event 0, it gets called like the next element in a sequence. So our sort of sequence counter moves forward when this sort of resets. And so our sequence learning is down here. These are the features that we are, oh, it's an E flat. And so we got the Beethoven thing going on here, I guess. And right, so this little section here is just displaying that during this rest, this time delay is quite a bit longer. We're ticking along further in time.
Of course, you're not showing the rest, by the way, Just
yeah, the rest is it's implied. Yeah.
Okay, well,
So,
people look at this.
There's
Right,
no like
you could
yeah.
right, whatever. You could
Yeah.
It's not accurate. So just don't.
Yeah, don't worry about
As
it.
long as we owned it, don't worry about it. But we all know that.
Yeah. Okay. Yeah. So I think that's. Oops, sorry. So the main thing with this example is we haven't incorporated space or locations. So it's sort of the passive example, but it should work basically the same way. So our features. Um,
We're just showing the timing mechanism. We're not showing anything
yeah,
else,
we're just
right?
showing the
So
timing mechanism. So this isn't our.
it's. Mhm.
Okay, go ahead.
Element
Okay.
in the sequence here is, could you remind me, this is in layer 5? What we're representing here?
Well, we haven't
Uh,
really decided where it would be anatomically, but I think we talked about it could be near the location representation, or it could be near the object ID representation. Like basically, it's which state the object is in.
The
This,
by the way, just the advantage of thinking about layer 5 is that if layer 5 is the motor output of the cortex, right? If a column just generically, just say generic, if a column wants to replay this sequence, you would want to act any kind of output is to replay this sequence. The layer 5 cells would have to know the timing. They'd have to know when to transition from one state to the next. And so just based on that simple observation, I would say our layer 5 cells are likely to get the timing signal. Now, there's a lot of stuff behind that I don't understand, but since those would be the cells that are actually, if I wanted to sing along with this, or if I wanted to actually do something with the same timing, the layer 5 cells have to have that timing information. So I would say that's at a minimum, layer 5 cells would be getting this information.
and this is like a 1D reference frame where it just
It's
shows
all
about the
it
position.
doesn't say anything else. It says no. It, we're just talking about timing itself. So there's some other reasons. What is the output supposed to be? Well, it depends on the melody. It depends what happened, where you are in the sequence. It's not just timing.
Yeah,
What we're doing
so
is decide. It's just saying, given I'm going to play a sequence of notes, what is the timing? What is the moment in time that note should be played? It doesn't say how I got to that. It just says, okay, somehow layer 5 is going to go through a sequence of notes or sequence of behaviors or sequence of outputs. And the timing signal just tells it more precisely when should it become active. That's it.
yeah, and I
Hmm.
guess the state representation, think of it as you can have a bunch of different states that the object is in, and there can be various reasons of why an object would transition from one state into another state. Like it could be an action that was applied, or it could be time that passed. And so in this case, it's just time that passed, so it is one-dimensional. But in other cases, it might not be one-dimensional. There might be you could go back in the sequence, or you could go from one state into various different states depending on which action you take.
Right. I guess even the word one-dimensional seems the system is not implementing a one-dimensional thing. I mean, a melody it has the same notes, different notes occur at different points based on the context of a lot of things. So
I guess,
anyway, I think we've said
yeah,
the same thing over and
with
over
the
again.
example of a song as well. I mean, it feels like with something as simple as a song, you could almost represent this just in L4 with the conditioning coming there.
Why would that would tell me potentially the internal thing,
So
but it
like
wouldn't lead to a behavior.
one feature predicts the next feature conditioned on time.
Yeah, but why would I want to do it there?
In terms of planning like motor output, like because I agree with you, you also need time to kind of orchestrate motor output. But I'm just
Well,
thinking, just in terms of like modeling, like what feature am I expecting next and when?
there's some big complications, and we don't want to get too sucked up into the neuroscience here. In layer 4, it's generally viewed that these are these spiny stellate cells which don't have apical dendrite. That was the classic view for many, many years. And now lately, I've read papers where they say, oh no, there's some percentage of the cells in layer 4 that are pyramidal cells, and they send their apical dendrites north. So it's possible that, you're right. Maybe maybe because I think the timing signal is coming in on layer 1. So it's possible, Niels, you're right. It's possible that that in layer 4, most of layer 4's cells wouldn't have this information, but some of them do. And it could be integrated in layer 4 somehow. But generally, layer 4 cells, most of them wouldn't have an apical dendrite.
Yeah.
Why would you do it in layer 4 and then not instead of layer 2, 3? If you wouldn't do it in 5?
Well,
Because I mean, layer 4, you have different features at different locations in the case of a behavior. So you'd have to make way more connections than if you represent the state in layer 2, 3, and then transitions
I guess
between the
I'm
states.
just a bit muddied for like an example like a song. What is the state we're representing? What is the feature we're representing? They seem kind
you're
of
right.
similar to me. Like I guess it.
Yeah, but I mean, we don't want to use a different mechanism for songs versus for behaviors.
I totally
No,
agree. I just think for the sake of clarity, it's useful to understand. Like, yeah, I just
I
think
don't
it's
think
useful
I
to
don't
distinguish those.
if layer 2, 3 is a pooling layer, I don't think you'd want timing up there, would you? It's like I have to have the timing on each note, and each note I'm assuming layer 4 changes, and each note I assume layer 5 and layer 6 are changing. So I'm not sure why I'd want timing on layer 2, 3 if they were stable.
Well,
Like
there
that.
would
That's
be
like.
there would be two representations. One is the state in the sequence, which is not stable over time, and then
But
the
isn't
sequence,
the
the
state
object
just the
ID.
current? Isn't the state the current note? And the current
Yeah, in
note
the
would be in
melody it
layer.
is, but in a object behavior, the state is like the entire object state. Like uh, the staplers, like there are changes at a lot of different locations, and you'd expect different changes at different locations. So layer 4 is really like what is active in layer 4 at different points in the sequence really depends on where you are in your reference frame.
Right,
So,
right. But that would be where I need to store the information for each of those
but
things.
then you'd have to store the transitions for every possible location on that behavior, versus if you just pool over the states in the behavior sequence,
Mm.
you only need to store transitions between behavior
Mm,
states at one place.
yeah, I'm not sure. Does that, it's confusing to me. Like when now we're talking about behavioral states.
Yeah, maybe the next slide that Scott has might illustrate a bit.
I thought that, yeah, maybe it's all right. Let's just keep going on. But I'm not sure I agree with what you just said.
Yeah, so in this example, the event is the closing of the stapler. That's how we start off with, and then so I'm just gonna restart this.
Wait, the event that closing a stapler, or is the event that the stapler top is moving? I mean, in behavioral
Okay,
models,
you're right.
it's
The event is that we start moving the stapler. The hinge goes from we go from the sort of static to we just start moving in this
so.
direction.
I'm sorry, I'm going to pick this apart. The word event. We're saying the word event means the thing I'm applying timing to. Like this is the thing I need to have timing associated with it. Is that what the word event means?
It's a
Oh,
real good
Vivian, you're
question.
muted.
Oh, the event is the thing that resets the timer.
Mhm.
Okay, fine.
But you can have a
Um,
kind of semi-continuous representation of time between that. Like, so you can represent the smooth transition of the stapler until it like clicks and staples, and then you reset the timer again. But you get like various inputs into layer 1 between it being open and being closed, which is like the movement through the
but I don't think
time.
so. There's analogies here to the music as well. Initially, can I go back to the music for a second? Let's go back to Beethoven's, right? You got da 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 da. Initially, I thought every one of those little notes has to have its own little timing signal, like you said here. I felt at some point I said maybe that's not true. That the triplet itself, da da da, could be one thing, and then the da, it's like you can play out a little mini sequence, I think, without having a time reset event.
Yeah.
Um, I'm not convinced of this, but I'm semi convinced of it. And And so the question there is like when the stapler is moving, there's clearly an event when the stapler starts to move. That's like, oh, look, something happened. That's like the note appearing. It's like the attack of the note. All of a sudden, the stapler starts to move. You noticed it right away. Bingo, something's happening here. But I don't feel like there's states in between. It doesn't seem like there's timed events as it's going down. As the stapler moves, it doesn't feel like there's a continuous set of timed events. So maybe this is what you were getting to earlier. I'm not sure. It's like,
Well, I think I would have said that there is a sequence of changes as it goes down, but they don't reset the clock because there's not one significant event. But instead, you have like you go through the activations of the different matrix cells, the different time cells. They just cycle through the activations, and they all still feed into layer one, and you
oh
can
yeah,
just make
right,
connections to the
right.
different
Oh,
activations.
right. Yeah, I'm sorry, I'm losing my brain. Yes, you're right. I forgot. Okay, sorry.
Oh no,
So it's like tapping your foot. You don't tap your foot on every note. You tap your foot.
yeah, exactly. Like in this
So-
melody example, I think the first time I showed this, we talked about, okay, maybe the reset is actually not each note, but instead it would be at the bars or the
Right.
main rhythm,
If
and
I
you'd
was
have
tapping
them
my
in
foot to
between.
this, to Beethoven's Fifth, I'd tap it on the beginning of the da 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 dum,
Yeah,
da
but
da
you can
dum
still
dum
represent the
dum
space in
da da da
between.
dum. So the fourth note would be a tap. The first note would be a tap. That kind of thing. Um,
Yeah.
you're right. So
And then in
um,
that case, how are we modeling time in the column, kind of dealing with tapping?
So
If a
the,
reset is happening before the next tap.
why would the reset happen before the next tap?
I thought we just said that the
it
reset
would
is happening after each note.
no.
I
I
just
think
said
it
it
was
doesn't have to happen at each note. It can happen just at the like 1 and the 3 beat, or just at the
Okay,
1
right.
beat,
Okay.
and then but you can
remember
still yeah.
in the brain. Remember that the evidence is that the duration of the cascade of timing signals is up to about a second. Remember that was a guy told me 800 milliseconds is typical. So anything that happens in that 800 milliseconds in that second can read off its timing. So the da 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 would all be under one sort of clock passage. So maybe the first note, so that little clock circle up at the top of this picture would go, you know, it would go around and several notes would occur at different points along there. Each note would be seven.
Right.
That's
No,
right.
okay.
Right.
Yeah. No,
That
I
that
think
makes
that
more
sounds
sense
good.
to
And
me.
right. And I
Right.
think that also fits with like having kind of a hierarchy of sequences or kind of behaviors. Like it just feels like that fits better with kind of chunking, um, where you
We
have
definitely chunk.
like
Yeah,
something
right.
happens and then repeats and something happens and then repeats. Um, because and then we're just
Right.
making better use, I don't know, of all the time cells. Yes, I think that makes
Yeah, I
sense.
think it's maybe better illustrated in the next example because I tried to show it more there that like
Okay.
um the time cells, that's why I added colors around the little circles. Like if you look at layer 1, the colored input changes, so it gets input from a different time cell. It cycles through those activations, and you can associate different changes at different locations to each of those. But we don't move to the next state until the reset happens, like the next bar in the pink on the pink line. So
All right.
yeah, you can
Right.
represent time between resets almost
Yeah.
continuously or to a pretty good resolution. But then yeah,
Right.
as when you reset, you go to the next state of the object.
So in a
Right.
hierarchy, do these share the same time scale, or is the time scale different for these time cells?
No, the time cells would be just one global clock, so you wouldn't have a different global clock for different levels in the hierarchy.
But
So it all
they
be
could
the
pay
same
attention to
time.
different ones. So like in a low level sequence, if it's like a very fast thing, it might use like short time cells, whereas a more kind of high level sequence would be kind of learning associations with the kind of the time cells that appear later.
So like
Assuming
the
that all
difference,
happens between a reset event.
so
I
the
don't
difference between these here is it's the same in different regions of the hierarchy, or is it like
Yes, they're all
Yeah, it
global.
would be the same.
Global.
Okay.
Right.
But it's up to a column, depending on when a feature is observed, to decide which kind of cell to associate with.
Yeah, but they all get the same input. And
Right.
yeah, the only reason they would learn something else is if they don't get input on the earlier time cell activations.
Right. And then, yeah, I guess this example is making me think, the earlier discussion about kind of how global this timing signal is and between different modalities and stuff. Because like with the stapler, the only way you can really kind of predict, like the stapler doesn't have like a fixed amount of time it takes to open it or whatever. That really depends on how you are interacting with it. So it feels like that's an instance where kind of almost predictions from your motor cortex about what is like the timing signal happening in the motor cortex are going to inform your perceptual regions about what they're going to see. So like if my motor cortex says, "Oh, we're operating at this, like I'm opening this thing or whatever, I'm moving very fast," then the visual cortex needs to be kind of ready and basically that fits I feel with having like a more global time signal.
Yeah, I
That's
think that's
interesting.
right.
So the motor
But
system.
it could be very simple. There doesn't have to be a lot of coordination going on here. If there's a timing signal available, if that timing signal consistently correlates with transition changes in the column, it'll learn it. If it doesn't consistently correlate with the timing signal, it won't learn it. And so if something doesn't have a particular speed, it changes all the time, well, then you're not going to learn the speed of it.
But then I guess is the issue, is that too restrictive? Because then it's almost like then we can only learn things like music. And I think like music is actually, and being able to tap to a beat is quite a unique behavior amongst like some higher primates and like cockatoos and stuff like that. I think most animals aren't capable of that. But clearly most animals learn kind of behaviors in the world, like how to catch a ball or I don't know.
Well, if it's a cortical behavior, I mean, we use it elsewhere. I mean, I'm sure it's used while I'm typing. I can type slower, I can type faster. I'm
That's what
trying
I'm
to think of
saying.
other.
Like that doesn't have a very specific time interval. But
Well, I don't
maybe
know.
as long as
I
it's
think
consistent amongst kind
I
of
think
cortical
I
regions,
think
then
no, I think it is. I think when I learned the type, learned that, I learned type old school. They had a metronome, right? They literally had a metronome, and you, you press your fingers on the beat, and then over time you learn a particular pattern. So that they say that the timing of your typing letters is very unique to humans, and that it's a spying technique. If they can see the speed at which you type on different letters, not just the intervals between each key that you press, if they can tell who's at a keyboard. So so it's like, I think we've learned, we're not aware of it, but you've learned the tempo of typing, and it's consistent for you, and you probably do it the same all the time unless you purposely try to speed up or slow down. So I'm trying to think of other examples where we have things are you have specific timing associated with them. I can imagine a tree breaking off a tree. I've seen this enough times where you hear a crack. That's the beginning of the limb breaking. And at first the limb doesn't move very rapidly, but then as it starts to fall, it speeds up, and then I can anticipate, if I looked at a tree, I could anticipate the speed at which that limb will fall as it swings down it's hinging on its broken part. I'm just trying to think through examples where I might have timing where I've learned that that it's useful. That's all I'm doing. Anyway, I think it's why don't we just say the timing signal available, and it's useful, it's useful. If it's not useful, it's not useful. I don't know. And if is there any holes in that? I don't know. Were you giving examples, Niels, where it didn't work?
No, I'm more just thinking that that maybe we can ensure that it is more useful by like if we have some flexibility about, like, I just feel like there's a lot of behaviors in the world that we want to learn that kind of have a consistent timing to them, but they're kind of dependent on how we are interacting with the world.
I don't know if I would say the stapler has a consistent timing. I mean, objects that are like behaviors that are contingent on which actions you apply seem to be like you don't need to care too much about the timing. You just care about which action you apply and with how much force
Right.
you apply it. We can even just bypass the timer in those cases. We just need a motor cortex to tell it, okay, I'm applying force to the stapler now. Expect the state to change.
Right.
Yeah.
I agree with
Yeah.
that.
It
I
just
think,
seems weird because, yeah.
in terms of this, the light switch problem, I'm not sure if we need time at all in this case. You know, I suppose if there was a delay between when you throw the switch and when the light came on, that would be required timing. You know, this switch always, we
Yeah.
have some lights in our stairwell, which are old LEDs, and they don't turn on for about half a second. It drives me
They
crazy.
flicker a little bit first.
No, they don't flicker. You just flip the switch and nothing happens. And then a half a second or 3/4 of a second later, they come on. I'm like, every time, and I hate it. I never use those lights.
Yeah.
But I know I can anticipate them. So there's a timing issue there. But normally, I think for our general light switch problem, I don't even know if we need to think about timing at all.
Order, I guess, was different than time. But yeah.
Right. Sequences.
Um, so just out
Yeah.
of just trying to be a good host here and knowing that Hojae's got a half hour and Niels
Okay.
has a half hour here and I went over by 10. So if that's all right, if I just kind of keep things moving along and
Yeah, that's great. I think
okay.
we just decided we need time.
Okay, great.
I proposed we don't need time. Sorry.
Not at all. Hojae, you
Yeah.
want to take the reins here?
Yeah. And I mean, I don't want to jinx it, but I want to go fast to get to Neil's point because I feel like mine, I'm kind of making, in some sense, a little bit blanket statements that I feel like we all kind of agree upon. So, I mean, we'll see. If
That's a
there's
double
controversy
jinx.
here.
You said it was both going to be fast and that we're all going to agree on the points.
Yeah, that's almost impossible.
All right, yeah, but I mean, I feel like it's not like quite tied to behavior. So I guess I want to actually get to the problem of like, I mean, that's my wish. So okay, so my topic was to kind of recap fast and slow learning
Okay, I think you're
and
presenting on the
importance of
wrong screen.
attention.
Hey,
What?
Hojae, I think you're presenting on the wrong screen. We see
Oh,
like
okay.
notes.
Oh, is there notes? Okay. Was there notes? I don't know. Anyways.
There's like a split screen between black and the presentation view.
Okay.
Yeah,
Is this better?
Yeah, no.
I think
That's
so.
better. That's better. Yes.
All right. Yeah, so kind of it like yeah, my topic was about the fast and slow learning and importance of spatial attention, which I guess I mean it's important but doesn't directly tie into behavior. So anyways,
Well, it does,
that's
I
even
think.
more.
But anyway, okay. I think the attention ties
Yeah,
into
that's why
everything.
we're talking about it because
Yeah. I mean, okay, well, yeah.
Yeah.
Anyway, so these are, I think, some things that we agreed upon related to hippocampus. So I have one side for hippocampus, one side for attention. So learning always starts from the hippocampus, which is you can think of it as like the highest in the hierarchy of columns. Hippocampus can rapidly lay down points of what is
I
currently.
mean, I think we said the hippocampus learns things the fastest and therefore first, but I don't think we necessarily said it. It needs to be learned in the hippocampus first, and then that teaches other regions. Like could be learned in the other regions in parallel, just at a slower
Right.
speed.
Right. I think saying it always starts. I would say learning always. When learning something through attention, you're always involving the hippocampus, but the other regions could be learning too at the same time, but slower. So the word that it starts in hippocampus implies that it moves from there elsewhere. It's more like learning always involves the hippocampus. I'll make that statement, see if anyone wants to object to it. Learning always occurs. It's like learning doesn't just occur lower down. It always occurs at least at the top of the hierarchy, and elsewhere is probably as well.
Okay.
Yeah, fastest at the top or in the
And it's faster at the top, right?
Okay, so I changed the starts to occurs, and I guess that I didn't add the fastest, but yeah. Bullet point
Yeah.
2, hippocampus can replicate down points of what is currently recognized at the attention location, and that can be lower level features or IDs from complex compositional objects. And then I don't think any that's agreement here. Hippocampus can be thought of a single cortical column with one reference frame actor at a time. Or I think so. This was a statement from like a ex Caldera a couple months ago, but then later we had also drawn hippocampus as multiple cortical multiple cortical
Right.
columns at different scales.
I think that's always in the back of my mind. It's the second one, right? It seems
Yeah.
as if, you know, the learning modules can work as individuals, and the only reason we have multiple ones in a region is to speed inference. So it just looks like the hippocampus is a set of single column regions, each one having a different spatial scale, just like in the cortex. So it's like mirrors a cortex with a set of regions, but each region only has one column, and they learn quickly.
But are both of these statements maybe both correct in the sense that we would have one of those kind of regions, one of those kind of columns be active at a given time? I'm just trying to think of an example where multiple of them would be simultaneously active.
We haven't walked through this a lot, and we haven't figured it out. So, but this is the stuff I've been working on recently. So, if you just say that the hippocampus is parallels the cortex as a whole. So the cortex is a series of regions at different scales that are connected hierarchically. Then the hippocampus has a series of one column regions at different scales. So it's like that's the big difference. And then because the hippocampus doesn't have multiple columns at each scale, it requires the cortex to feed it pre-inferenced objects. Otherwise, it would be much too slow. So if you can follow that, I can leave it at that. It's like a parallel neocortex, where one column per region, and it's relying for object inference, or what is the child being fed into this hippocampus is going to be inferred in the cortex mostly.
Yeah,
so like I'm at the.
Sorry.
Go ahead.
No, I was going to say I kind of like the term of the mental scratch pad, where it basically gets inference from lower down, and it can quickly lay that down, but it doesn't learn like the lower level objects and the composition of them and all that from scratch, and then infers it from scratch on its own.
Right. I don't know. This word scratch pad never worked for me, but if you like it, we could use it. But think about it. I'm looking at the intersection, and I see a car and a person and a bicycle and a sign. Those are all being recognized in the cortex proper. And they're being fed to the hippocampus, and the hippocampus says, oh, well, look, I can just say the car is here, and I can say the sign is there, and because I didn't have to infer it. So if that's what the global scratch pad meant, then that's a good term for it. Right. And if something can't be recognized in in some attended region, then the attentional area gets smaller until something can be recognized, and then that's what's fed to the hippocampus. Anyway,
Yeah.
we haven't really gone over these ideas. It's not clear for our task next week whether it's important.
Exactly.
I think we need to have the idea of it. We probably will have to have the idea of attended areas, but it's not clear to me that we have to have, we don't have the same learning problems that brains have. That's the rapidity problem. Monty can learn any speed it wants. So I don't know. We may not have to get into this hippocampal theory next week.
Yeah. Okay. So I think what we have just said also kind of touches on the last 2 bullet points. Temporary model can be used to invoke predictive models at lower levels in hierarchy and to interact. And inference can be extremely fast if receiving unique child object IDs, which, yeah.
Right.
But
That's the
yeah,
last
that
point. It's like,
doesn't just apply to the hippocampus. It could also just be higher level regions in the neocortex.
Yeah.
right.
All right. Some agreed upon, or what I thought were agreed upon statements about attention. We always pay attention to one volumetric space in 3 at a time. And the region is broadcasted globally. A region can only infer one state of an object at a
By
time
the way,
by
by
attention.
the way, I'm not sure it's broadcast globally. We have to be careful of that. It's a global thing, but it may not be broadcast at all. It may be just subcortical, like the supracolliculus. It's like there's a map of space on top of the supracolliculus. What's important is that each column somebody knows where each column is in that space.
Yeah.
I
I
don't
think
think
that's what
I don't think the columns themselves need to know that. Someone else could know that. Anyway, it's unlike timing. I don't think this is broadcast. I don't think so, but I don't know, but I don't think so.
Yeah, almost like more like a filter than a signal.
Right. It exists
It's kind of like
elsewhere, and
some columns will be captured within this space and some won't. But
right.
it's
Yeah.
And
but it's not
the
like
columns themselves
a-
probably don't know that. They probably don't keep track of where they are in this global space. I mean, a morphology column doing an allocentric object probably doesn't have any idea where. It doesn't know where that object is in the world. It just says, oh, it doesn't know where the object is in the world.
I think
Yeah.
one
Someone else might.
interesting idea we we discussed, like if it were possible to broadcast that signal more, is that it could allow kind of parallel learning in columns or inference in columns that are currently not getting input, like if you draw something on someone's back and at the same time visual columns are kind of visualizing that movement in space, the attended locations on the back, to basically trace out the morphology and recognize the object. And so even though the back hasn't learned models of a letter or something, the visual columns could recognize them just by knowing where in space we currently attend to.
Right. I think there's a lot of things we don't know here. I don't
I
even
also
know what
wonder
it
with
means
that
to
example.
broadcast attended area. I mean, how do you broadcast an attended area? I can broadcast a
Right.
location, but an attended area is almost like a set of points, and I can't broadcast a set of points.
Yeah, I
Anyway,
wonder whether
I
the
just
back example. Sorry.
go ahead now.
I was just saying, I wonder whether that could partly be done with hierarchy, where you just have a certain level. Because I mean, that's a very difficult thing to do. I feel like, yeah, and whether whether it's hippocampus or some other high level region, that's kind of getting some abstract notion of movement from lower level columns. And I don't know.
Yeah, I guess
Rather than relying, it's not like a V1 column or V2 columns, like, oh, that's a letter H.
Yeah,
more
maybe
like,
it wouldn't have to be broadcast globally. Maybe it could just be sent to the hippocampus. But just the idea that if someone who has all the models would get information about where attention is in space, that could help recognize stuff just based on morphology. Or, yeah, some kind of way of models learning morphology, columns learning morphology models without getting input directly.
Well, do we have to deal with that problem for next week?
Yeah, no, we don't.
no.
It's just,
Yeah.
I mean, I love that problem. I think it's an important thing. It's going to give us insights about a lot of stuff. But not clear.
Vivian, is that what you were saying about attended location in 3D space can be used for morphology-based learning and inference in columns that don't
Yeah.
receive input? Okay. Yeah, I guess I was thinking the other way where a column may be receiving inputs, but because it's not in the attended region, we're getting inputs, but we're not actually learning anything. Like if I'm
Yeah,
focusing
but that
on,
doesn't. But That's right, but that doesn't solve our learning problem, right? That just says,
Yeah.
oh, these guys just aren't being very active right now.
Yeah.
We don't, we're not, we're ignoring them.
Yeah.
Um,
Yeah.
uh, right.
All right. The end.
Cool.
That was
So
less than half an hour. I think that was the quickest one.
yeah, yeah. At least
See, I
that
told
one
you.
wasn't jinxed.
Maybe we're just getting tired.
No, I mean, well, I guess I really want to get to the next point. So, I mean,
Okay.
there's actually, so in preparation of
Wait,
this,
wait.
I watched.
Now you gotta go over it. See, now we just said we're done, and now you're
Fine,
showing
fine,
up
fine,
again.
fine. All right,
No, it's
fine, fine.
no, James. I think it's fun. I'm joking. Go ahead. What were you gonna say?
I mean, in preparation of this, I watched at least like a good half of all the meetings since the November brainstorming into X feed. And there's actually a lot of questions. Like if we go into detail, which is why I did like this putting together was a little bit hard because if we write statements like this, like okay, kind of sounds good, kind of true, but like there's actually a lot of questions. I feel like if we actually dig into it deep enough, but I feel like this is not the right kind of way to discuss it. So hence why I didn't want to like kind of spend too much time unless
No,
you have to feel
there's
confident with
always
that.
a lot of questions. The way this
Yeah.
progress works is that the frontier of what we're working on is always filled of unknowns and weird things and questions and mysteries. And then as you move forward, they get resolved. But then there's another set of big things, unknowns and mysteries. It's like you're
Yeah.
just shoving them into a
Yeah, like
funnel or something.
it's interesting how with behavior and time, like in my head, those were quite clear, but at the same time, there is still a lot of kind of stuff we still need to iron out.
Right, right. But then some
Yeah.
things become really set in stone, and we can build them. So that
Yeah.
everything
Yeah.
this all happens like that.
Maybe
Yeah.
one last point around attention that I think maybe wasn't on the slides, but I think was at least for me, a clarity thing that came out more during the past months was that you kind of narrow the attentional window more and more until you recognize something. So if you can't recognize the large thing, you narrow it down more and if you can't recognize that, you narrow it down more. And yeah, and that
That
might
that
correspond to going to different levels in the hierarchy at the same
It
time.
would go to different, probably, because that goes back to the hippocampus again, right? Because remember, the hippocampus has to be fed complete objects. And if it can't, if it says, oh, what's going on over here? And if it doesn't have a complete object, it gets smaller and smaller and smaller. And probably, well, the latest thinking I'm having is that moves down both the hierarchy in the cortex, but it also moves down the hierarchy in the hippocampus. Like, okay, so we got to go down to these two columns that are saying what's going on here. Um, and then eventually you get to the bottom, you get to a line or an edge. And if you can't do that, then you're looking at like white noise and you go crazy. Literally.
Yeah. I mean, we also said that behaviors are not compositional. Like, there's no such thing as compositional behaviors. I don't know. I mean,
Or
it's
I
kind of
think we've
interesting.
never come up with like a convincing
Yeah,
example of where we need it to be. But
But
right.
they can be compositional, like the only
I mean, they could.
they can be part of compositional models,
Right,
and they
right.
can get input from like changes in morphology model location orientation, but
Yeah,
behavior models seems like we wouldn't have
Well, I
to.
think
right.
Niels said it
Yeah,
right.
yeah,
We couldn't come up with an example. Mechanistically, it would fit, and mechanistically, just like composition and morphology, could
Well, I
work.
think mechanistically it would also not fit because the definition of the behavior models is that the input to it are changes, but the behavior ID is a static feature. So by the definition, it shouldn't become the input to a behavior column.
Uh,
Would it be the change in the behavior ID?
Yeah, I think that could be an input to
yeah,
a
I'm
behavior
not sure I
column.
100% agree with you, but I don't think it matters. I think we can mechanistically, in my mind, if the connections could exist, whether they've learned anything or not is an interesting question. And
Yeah,
um, but we didn't think of any examples where it was clearly necessary.
yeah.
Do you disagree with that? That mechanistic? When I said mechanistically, I
Well,
meant
yeah.
like,
I think
yeah,
mechanistic, I mean, for sure, the behavior ID will be the input to other columns, but then we don't call those columns behavior columns anymore because they're getting static features as input. But I guess, yeah, the change in behavior ID could
Right,
be the
right,
input to
right,
another column, and that would then be a behavior column. But I don't know in what case that would actually happen and be
right,
something we
right.
learn.
Okay.
So yeah,
It's
yeah, I
semantic.
agree.
It's semantics. That's
Mechanistically,
fine.
like we know what could happen. Like yeah, the connectivity can be
The
there.
line, the neurons could go there. Whether they do anything is, not,
Yeah,
maybe not. Anyways, it does. The point is, we don't have to. You wouldn't necessarily have to change any protocols or. Um,
right.
it just, yeah, okay. I always like
Okay,
to think in
so
the brain that the connections exist, and if they're not useful, they go away. Because there's a lot of evidence for that, right? That's how it works. So, like, you could have all these connections going back and forth, and the brain at birth doesn't know this is the behavioral column or what other column. The columns don't know it. The cortex doesn't know it. Nobody knows it, and they just get these inputs, and some of them turn into behaviors, and some of them don't, based on the nature of the input. And some connections, hierarchical connections, make sense, and some don't, and those are lost. That's how I like to think of it. So.
Right.
so
In an
uh,
alternate universe, they might exist. They might be useful. 3D or 5D, something or other. Time warps. Sorry, Trent.
amazingly, I think we're doing just right on time here. So
See, Hojae was ahead, and she brought up a topic again. Now she just
yeah.
you don't finish early.
So I
Okay, but you
think
did on time. Good.
yeah. Nils, you want to take it away and move us into the final
Yeah, sounds good.
quarter?
Yeah, so I guess this is getting more into the meat of it, because yeah, just as a reminder, kind of for the focus week, the questions we're going to be trying to answer, at least that we last kind of agreed on, was how does a column use a learned model to choose what action output to achieve a desired state? And how do multiple columns, where necessary, coordinate to achieve this desired state? And the problem that we were going to focus on that we thought would be most fruitful is this kind of turning on a light switch. But I put in here kind of, I think if we feel like we have a reasonable solution to this, then a nice exercise would be to take that same approach and see if we can apply it to some of the other problems we've discussed, like the opening and closing of the stapler, or maybe that keyboard typing problem. If people remember a while ago, we had this whole thing about typing on a keyboard with certain characters and coordinating and stuff like that.
I don't think that was a very well defined problem, was it? I don't remember that being.
There were issues with it. I mean,
I I,
or
I don't I, I don't have a good memory of what
or
that
copy
is.
making. Yeah, yeah, we would definitely we'd re-describe the problem if we were gonna. But
But
my
yeah, I
point is
guess
just that,
the point
yeah,
being, if we have a solution to the lamp, we want to try and apply it to some other
yeah, we should
examples.
try and stretch it
You
and
know.
stress test it.
Are we
Um,
doing the lamp? Is it make sense to do? Does it make a difference between a lamp and a switch on the wall and a light on the ceiling? Because when I think about causality, I was always trying to involve two separate objects. Where when you have the
I
switch
mean,
on the
I
lamp,
still
it's
think of them as. I guess I like the lamp because I feel like it's both. It's both separate objects because there's a switch and there's a light bulb, but then they are hierarchically associated in like a higher level model, which is the lamp. Which
right,
I mean, you
right.
could
But
argue is also the same with a light and a switch in a room. It's just the room
well, I
that's kind of
don't.
the parent object.
Maybe I don't know. That's interesting. I like this. I like this. I've talked about the switch on my kitchen island and the pendant lamp that's above it. I like that because it's really hard to imagine them as the same object. It just doesn't ever feel like, oh, there's the lamp switch counter object.
Okay.
I I know where they are relative to each other, but um, anyway, that's the only thing
Yeah, I mean,
about the
because it's your
lamp.
kitchen. Yeah, I feel like
It's
they're kind of similar, but I guess I also thought with the lamp, like if we solve this or like if we solve part of this problem, I think it'd be interesting to think through like, okay, well now you see a different lamp with totally different morphology. You don't know where the switch is on it. How do you kind of know where to start looking for the switch or even that you're meant to look for a switch and things like that?
right, right. So sometimes you'll look for the switch on the lamp, but then if you don't see one, you'll look for it on the wall.
Or the
Um,
cord or yeah.
a cord, but even someplace else in the room, right? Then you go, oh, there's a wall switch probably for this lamp.
Yeah.
Um, I guess I just want to be careful. It, the lamp example, like here, it seems like the location of the switch being on the lamp is actually has almost nothing to do with the problem of learning how to turn the light on with a switch.
I agree.
And
Yeah.
and so the fact that we might say, oh, it's a child object to the lamp, but it could be misleading. That would, I mean, we can do this, but I'm going to be constantly fighting the temptation to think of this as a single object that has a behavior, when
Okay.
I think it's like two objects.
I mean, I
And
think, Niels, how you drew it to the right, it is kind of drawn as a switch and a light bulb. So maybe that's a way you can also think about it.
Yeah. I mean, I'm happy to, like, I definitely think that it's separate objects, but yeah, I'm happy if it's just clearer to show it as a light in a room.
Right. I mean, I think the lamp is a fun one. I liked it when you first brought it up, but I do think it has that risk.
Yeah. Okay. So maybe at
'Cause
least to start with,
because
we
most of the causality things we learn are not things on the same object. You know, I don't know. A lot of them
If we
aren't.
Yeah.
if we think about the setup, I mean, so in this switch on the lamp, we're kind of thinking, in my mind, I'm thinking, two columns hierarchically arranged. If I think about the switch and the separate light bulb, then I'm thinking about two columns, not hierarchically
Or
wait,
arranged
so
maybe not two
necessarily.
columns, or
what would
one
what's the
one
parent
column.
object? Why would the light bulb be the parent of the switch or vice versa?
No, I think she's saying there's a column that represents the lamp and one representing the
Right. But I
switch.
think that's what's
Yeah.
nice about this is we like there's multiple elements to this problem that we need to eventually explore. You don't need that lamp column to do behaviors, but maybe that's your concern, Jeff. But
Right.
I don't
Right.
know. I feel like it's no different than the hippocampus or the scene column or whatever in a kitchen. But I'm happy to
I think you just
represent
saw
it.
it there with Hojae's comments, right? There's no reason, and you look at a picture like this, you think, oh, there's an object called the lamp, and then the bulb and the switch are children of it. But that's not really important. There's an object called, and so we don't need that. We have an object called the switch, we have another object called the light bulb, and they're causally tied together. In the real world, those things may not be in a fixed relationship. They could be in different rooms. They could be, you know, as I mentioned, like the use of a remote control that moves around. So I think it's dangerous to easily fall into, it's like, oh, here's a lamp. We're modeling a lamp that has two things in it.
I mean, we could also
No,
just talk about the light switch and putting it in a different position, because
right,
that's
right.
already applying an object behavior and changing the state of an object. We don't really need the lamp.
Well, if we wanted
But we need a
to,
bulb, don't
well,
we? Or
if
what do you
we
mean?
wanted causality, if we wanted to, I thought the whole point of learning causality is we had a lamp someplace and a switch someplace, and you had to learn that switch controlled the lamp.
Well, you also
Um,
have to learn that if you apply pressure to one side of the switch, it will change its state.
Yeah, I feel like that's a
right.
different problem, though. I feel like that's kind of the column bottoming out and recruiting motor cortex.
I don't know. Would it
I
be? I
kind of
mean, you
agree with
still have
it.
to
I feel like
learn.
we should start with Vivian's proposal, like just one light switch and apply kind of at least walk through it so we have a solid idea.
Well, I think
And then the
you're
next
going to
level, like put down the lamp for the
maybe, but
bulb for the causality.
it does feel like I'm not sure there's any causality involved in the lamp switch itself.
I think
It's certainly not
I think it's the
obvious.
same learning mechanism, but I feel like that's happening within a column versus across columns. But yeah, I feel like, but should
But then I feel like
I'm
if we
happy
don't
to.
understand how that works, it will be difficult to solve the next step of the problem. But
Well,
I mean, I
I
feel
think we need to solve both, and
yeah.
I think it's going to be a related
The
solution.
switch has to have a morphology model in two states. It has to have a behavioral model. So just on its own, you have to have that. And then the light isn't necessarily a separate column. It could be the same column, just now inferring a light, but it could be, could be a different modality, I suppose. And now that has two states, on and off. And so, but these could be across modalities, so that suggests that there is this layer one projection that, we can learn causality between modalities. I liked it for that reason. It just felt like, we're going to force ourselves to think outside of a single column. Like Niels was saying, hey, we could do this all in one column, perhaps with the switch. It seems
Yeah,
causality is something that has to be learned across modalities, in long distance projections. And it can work locally too, but
But could we do it in one column if we need a morphology and a behavior model?
no,
Or
we'd
would
have to
those
have
be
a
in
behavior
different
model
columns?
and a morphology model. But one column could do the switch and the light bulb.
Yeah.
Yeah. Okay, well let me let me see if I can find some areas of common agreement. So current principles, behavior states represent an evolving process. So something is happening. I think this has been kind of a recent change in our language that we've focused on this, that behavior states aren't keyframes in that sense. They are describing kind of an evolving process. And then columns are going to project their active behavior state widely. And it's been discussed this could be happening by L3 to L1. And that this is likely essential for learning kind of flexible ways to achieve goals, like multimodality, like you just mentioned, Jeff, but I think just in general. Um, and then at various points, a column can bottom out. I find this
What does
very
that mean?
useful, yeah, but I
I
don't know,
don't know.
but and project directly to motor regions. So
What
to
does
achieve
bottom out mean?
So what I mean by that is I like you can think of all these kind of behavioral states being passed around and up the hierarchy and laterally and all this stuff. But when the cortex projects, when a column projects to motor regions, it's exiting the cortex. And in that sense, it's actually invoking motor, subcortical motor regions. And that's what I mean by kind of bottoming out, is that up until that point, we aren't actually changing the state of the world because no muscles are moving or anything like that. Um,
But if I'm flowing the switch, that or I'm opening a stapler, muscles are moving.
yeah,
That's what
because
he
you
means.
bottom out at some point.
I don't know, bottom out.
I mean, maybe we don't use that term. Maybe we just say they can project subcortically.
Okay,
Right,
but
that would make
isn't that
sense to me.
helpful? Like, I just feel like
Bottom out
just this
sounds like
mental
I've
image
reached
of
the
it, it
end.
could take a
I can't.
while. Like, for example, making coffee, like you might be going through like a bunch of different columns before you bottom out and actually trigger something. You might have like multiple different columns that bottom out, then come back to doing kind of
Again,
kilometer stuff.
bottom out implies to me that some processes stop, you're stuck, and then you exit. Where
I mean,
I
you
think
kind of you temporarily exit. You send an output, and
why
then
why why
until
can't why
you
can't
get
why can't they
okay.
I can't why can't it be going through a cortical sequence that's simultaneously projecting subcortically as it goes? There's no stopping; it just goes.
To me, bottoming out sounds quite negative, and I just Googled it, and the definition is literally to reach the lowest or worst point, usually before beginning to improve. So I don't know if we
All right,
want
Okay,
right.
so
So I think
let's say
Vivian said a
all
column.
columns
I don't see
project.
even at some point. I mean, there is at any point it's possible a column could be projecting subcortically, behaving,
Right.
generating some
All
type
columns
of
project,
behavior.
right? At some points they will um, send these
What
signals.
I don't think
So
we understand how that works yet. So at
I'm
least I
not
don't.
suggesting we understand how it works, but I think we can agree on this that they
Yes,
do it
that
and it's important.
right,
This is true
right.
for higher regions, right? Higher region columns can also send subcortically
Exactly,
motor.
yeah.
That that's what we've been told.
But yeah, so to achieve goals, everything's either kind of behavior state and how those are causally interacting or an action. And I feel like it would be useful to define kind of an action as a direct motor output. So this is an L5 projection. Um,
You know,
or have
this
some
idea.
sort of word that captures the distinction to just a behavior state.
All right. Um, this gets back to the attention window or the attentional area. I used to think that a column would project, like a visual column would be projecting someplace that would make the eyes move. And I don't think that's right anymore. I think the column is saying where it wants input to come from, and that is projected, say, to maybe a global map of the space, and then how that input actually gets routed to the cortex could vary. It doesn't have to go back to the same columns that requested it. It's basically saying columns are
Agreed.
saying move here, and then subcortically things decide like, oh, how am I going to move there? What am I going to move there? It's not. There isn't just one-to-one correspondence with a column and some motor output. It's like the column goes through some sort of space of saying we want to move something in this space,
Right.
and
Yeah.
so I just think when we think about the output,
Yeah, that
it's
maybe
even
action is not
even
the best
though
word.
I
even the
think
word motor output is misleading. It's not wrong,
Right.
but it's
Yeah.
I mean,
misleading.
before we talked about it as a target
Yeah.
pose.
Right.
So like a pose that you want to get as input in the world, like in egocentric coordinates.
Right, but
but
it may be that it's done. I'm seeing something, and the target pose is the finger. The finger moves to that location. The visual cortex is saying, we need to move to this location to push this button. But the eye isn't going to go there. But the finger's going to go there. So
Yeah, I wonder
you know,
whether
yeah.
maybe something like motor target.
I mean, in our previous discussion, we kind of talked about whether the action should be defined as movement in the object's reference frame. Like, I want to go to this point in the object, and then there's some conversion to egocentric,
right.
space, so that we can actually
So
carry it out. So
right,
there's like a
right. But
separation.
so I think that's right. The cortical, which if we have a morphology column, Hojae, it's representing an allocentric model of an object. It doesn't actually know where the object is in the world. It just says, and it says, I want to now go to this point of the object, maybe where the button is. And so it starts off by saying, here's how to move to that point. Then we've speculated that gets converted actually in the layer 5 cells themselves into an egocentric movement. The orientation is changed because the layer 6B projects to layer 5. And so the actual output of that column would be a movement in allocentric space. Egocentric space. But it's not saying how the column itself doesn't decide who's going to move there. It's like it could be
Right.
the finger, it could be something else.
Yeah, and I feel like this
Um,
is one thing we've never really agreed on is like, are motor outputs a target location or a movement, like a displacement? Because
I
I
think
feel
another
like we've
thing.
made like interesting arguments for both. And
Well, I mean, I think it
well,
doesn't really matter for the mechanism. No.
that's what
Oh,
Vivian's always tried to convince me, because I think in the brain it's going to be a displacement, but Vivian says it doesn't matter. We could do a location.
I feel
So
like it does
I
matter for
don't
this
think that.
topic. Like if we want to think about like how we're actually going to turn on the switch, I think it is worth thinking through because you could for example imagine, okay, yeah, we're just going to recruit motor primitive, which is like a flicking motion at a location, or the cortex has more control and it actually can say, no, I want you to make this movement. I think, yeah,
yeah.
it feels
So also last time we also talked about emitting goals and not necessarily actions. And we had a lot of confusion about what goals could be, or whether it's a location or like a movement displacement. So it's not that the column is outputting like any motor output or do this or do that. It's like, I want to get to this state, like state 1
right,
to
well,
state 2, and we'll
yeah.
figure
I mean,
out
we've
what the
talked about
action
goals
but
is.
for ages. I feel like
Yeah.
in our current language, like the behavior states is doing
The
a lot
goal.
of goal stuff. But
Okay.
yeah, but the motor target
Yeah.
is maybe
goals
also kind of like
goals
a goal.
goals are all in the cortex, right? We don't send goals subcortically. If
But I
that's
mean, we might be
definition of
sending
goal,
something similar to a goal. Like if we do
I
have a
think.
motor target, like, oh,
Well,
attend
that's
this
right.
location, you could look at that. You could
Well,
describe that as a goal.
it's totally at that point when it gets subcortical, it's model free. It's just saying, go here, right? it doesn't know why it's going there. It just says go there. The cortex knows why it's going there, but the muscles moving the finger and the associated stuff have no idea that they're putting on a light switch.
But
Um,
I guess the definition of a goal would not be that it includes any model knowledge. It would just be a target location and orientation in
right.
space.
That's why I think
So,
using the word goal is misleading.
well,
Um,
okay.
This is maybe a more minor question, but I'm collecting open questions, and the list is
Nice.
growing.
Nice. Yeah. This is. I think we can definitely start off from here for the focus week as well. This is really
Yeah,
nice.
I wasn't thinking we would necessarily get through all this stuff, but I think that's totally fine.
Okay.
I think this would be a useful exercise to start on Monday.
Yeah.
I think if we can just establish the current principles, then I'll be happy.
So
That might be the whole
very
week.
easy.
So yeah, maybe
All right,
just to
let's
zoom out
do this.
before I keep going. So yeah, I was just saying, Jeff, that yeah, I don't imagine we'll get through all of this today, but that's fine. I think this will be a useful exercise to start us off on Monday, going through the rest of these. But yeah, so I've got current principles, notations on causality and forward versus inverse models. I think agreeing on this could be helpful.
By the way,
And then-
where's this document?
This is on Excalidraw. I shared it.
Oh, okay. Oh, great.
Yeah, I shared it on Slack just before this meeting. But so
Okay,
I guess the other advantage, if we go through this more on Monday, is people also have more time to go through it and add comments and but yeah, tried to summarize a description of learning as including the forward model and potentially how the inverse model might work, and then open questions, and then kind of just a brief recap of some kind of further ideas that we can maybe return to. If there's anything I've left off here that someone has proposed that they want added to the list, feel free to add it.
Can I just ask this? The overall goal of like turning on a light.
Yeah.
Can we be a little bit more precise about that? It's like, do we want to see a situation and I say, I need light, how do I get it? Or is it a situation I say, I see the light and I think about turning it on? Or is it like I see the switch and I flip the switch and I'm just trying to.
Yeah, no, that's a good question. I think the way I was thinking about it was we start with the assumption that we essentially receive the goal light on. So whatever column is representing light, it's been told you should have light on. And then the question is, what are the representations and associations we need to have learned in order to act on that and actually make it reality?
So I don't know what, say the goal is to turn the light on. Like someone tells me, Jeff, please turn the light on, that kind of thing.
Yeah, or yeah.
Yeah,
Or
it
could be a curious child who has seen the light going on, and now they're imagining light on, and they're curious how that happens. And
so what I thought of it, what I proposed before, that this wasn't like some sort of global goal. It was like you could see the light. You've already learned that the light has these two states, and then you imagine the like some internal that column. You say, oh, there's the alternate state. And then by imagining it, you cause it to happen, as opposed to some sort of like, I don't know how to broadcast a goal, like I want more light across the cortex.
No, I'm not suggesting it's a global goal, but I guess I'm just thinking, like, imagine we have a switch column and we have a light column, and then
a switch model and a light model.
Yeah, I guess they could be the same column.
Right.
And then these project subcortically. Basically, the light model is going to receive that we want to be in the illuminated state. And then the question is, what association do we need to have learned between the switch and the light? And what do we need to have learned about how motor behaviors, like whether that's motor cortex or subcortical, how they influence the switch in order to turn on the light?
Wouldn't we need to have, we'd have to have a visual column of the light, a visual model of the light. We'd have to have like a visual model of the switch, maybe not, or tactile model of the switch, or
yeah, I guess I'm assuming for this that like the subcortical projection could kind of project wherever it needs to. Like
I'm just trying to understand the model.
Yeah.
do I need it's on the model of the switch. This is something we haven't really talked about, is like, I could have a visual model of the switch, but I could just see it magically goes up and down. But would I have to have a somatosensory model of the switch too? I mean,
Yeah.
Yeah. Yeah,
uh,
I think we
we
have
need
talked about this
something in
because
the motor
it gets
cortex.
complicated. Right.
Yeah.
It gets complicated, and like, yeah, I remember we talked about it in the context of like picking up an object. Like, who knows what the morphology of a cup is, such that the motor cortex can appropriately like shape the hand. Um,
mm,
like, because we don't want to pass a model around. Um, and so yeah, it does get complicated. I think part of the hope with this problem was to maybe avoid some of those issues, but
well, I'm wondering, maybe you avoid some of those issues as to, I'm sitting here thinking like, well, moving a finger is a complicated thing, but I could, there's a lot of things we talked about could make the switch go. You can,
yeah,
or the
like
light
I
turn
think
on. You can
you get the example of
a
like
sound,
Alexa, right? Yeah, and so that's
right?
kind of what I meant by the subcortical system kind of projects to whatever it needs to, maybe at
Or
least
even
first
like,
blush. So like if
right.
that's making a vocal utterance or whatever, um,
Right. We want to get to the very, very generic description here. And the very, very generic description is not necessarily a finger moves the light, but there's some action someplace. It doesn't matter what it is. It could be any action that is um that's been observed and then can be invoked. All right. Well, it's going to take a bit of thinking. Um, as I always say that the key to success here is defining the problem very, very precisely or correctly or
right,
in the right way. So we don't get hung up on confusing, you know, side problems.
right.
It's really
No, I
challenging.
think it's a good point. Yeah, so I've written for now under the question. So yeah, assume an LM receives the goal light on. Um, and I think we should assume for now, like the opening version of the problem, that subcortical motor regions can handle something like a vocal sound to turn on the light, or a flick motion at a location in space. Like that we just kind of need to recruit some basic primitive. But we still need to learn that that's the primitive that we want to do. So it doesn't make the problem super easy. We still need to learn that, okay, that's the motor primitive I need to recruit to turn on the light. But we don't need to like coordinate the hand moving through space or whatever.
Yeah, yeah.
Um, okay, well, so then the last principle I had, which I just thought worth was stating, is that yeah, pretty much all learning is going to be Hebbian. So relies on the fact that we have kind of a globally focused attention to basically sparsely associate some sort of representations. And because it's Hebbian in the true sense, then that Donald Hebb also meant, and like STDP, then temporal ordering can be used to learn causal relations. So it's not just a bidirectional association. It's A causes B, and I'm going to learn that association or like that
Yeah.
relationship. Um, but that some amount of reinforcement, i.e., learning, i.e., dopamine signaling, might play a role, but that this should probably be minor because rewards in the world are sparse. We haven't talked much about this. I think, Jeff, you've brought it up once or twice, but I feel like reinforcement learning is a pretty heavily studied area, and clearly it happens in the brain, but it also, clearly has its limitations when it's the kind of predominant learning paradigm. Um, like
Yeah.
I think the way we're going to go beyond what reinforcement learning can do is by focusing on all the Hebbian learning and all the model-based kind of representations that are being used. Um, and yeah, so this kind of reinforcement learning hopefully is just going to be a tiny part.
some point in time it would be nice to do a contrast between reinforcement learning as it's studied in the brain and reinforcement learning as it's studied in machine learning techniques. Because I have some very specific things I read about, neurons and sort of that are reinforcement like. But it may not be the same as what's going on in machine learning. I was like, I don't really understand deeply why reinforcement learning is what its limits and difficulties are in machine learning. So, I'm just saying I think there's a disconnect perhaps how those words are used
Yeah.
in the two different
There were
fields.
some good presentations from some of the other people in the group, and I'm sure Vivian could talk a lot on the subject. But yeah, I guess you were saying in terms of limitations. So yeah, I mean, one of the main ones is just the like where do these rewards come from that reinforcement learning tends to rely on, and how do we have enough of them to learn? So I think what's nice about what we're doing is it's more like Tolman's rats, where it's like we learn these models through exploration, um, and kind of the use of maps, and then if there's a situation where we might get a reward, then that can help us kind of reinforce certain behaviors and things like that. But most learning isn't relying on that. The way
Yeah,
reinforcement learning tends to be used in machine learning is it's like the predominant, if it's a sensory motor setting, it's like the predominant way that representations are being formed, and then you're just relying on kind of error back propagation to um,
right. All right. I think it's beyond me for today. So, um,
but yeah, so I won't have time for all this. Yeah, maybe I'll just quickly show this diagram just so that when you guys, if you're reviewing this offline. So this was combining, I don't know, was that you, Vivian, who made this from the previous, when I was away in November? You made like something
Yeah,
like this?
I made the light switch pictures or added those, but I don't know if did you add the column diagrams?
Yeah,
Or
and I modified this slightly
yeah.
because I think this was before we talked about, at that time, state was a bit more like a keyframe. So I've tried to emphasize here that one state is switching on and another state is
Uh,
switching off.
yeah, I mean, I think in that case, I would show the kind of change arrows and not the morphology of the light switch in the two frames. Because I think when I made those figures, there was like the morphology model is the light switch itself, and then the goal is to get into the different state of the morphology. But then the behavior model would just be like the changes that happen in
Yeah, so
the
as in you would
light
show
switch.
it like this is like a movement happening in it.
Yeah,
Yeah. Yeah, you could also do
if
that.
that's the behavior model.
Yeah, this is a behavior model. I mean, yeah.
Because the
Are we gonna
behavior
call
model
are we gonna
wouldn't.
call the light model a morphology model? I don't know if that's a
I
well,
would.
distraction to worry about that,
I think you
but
have both. I mean, aren't
yeah,
these?
personally I
Yeah.
felt like it was fine to call it behavior model, but
Yeah, I mean, I
Well,
think in both cases you have both. I don't think the behavior model of the light switch would include things like the 0 and 1 that's printed on there and how the switch is shaped and all that.
yeah, I wasn't
But
trying to show that that was part of the learned model. This was meant to be kind of an abstract representation of what this is capturing,
yeah, but then we
but
would
maybe that's
have a
not clear.
morphology model of the light switch in both the states,
Right,
and similar with the light, I guess.
right.
Even though with the light, we could argue that there's just a morphology object with two states.
Yeah.
well, you
But
could,
I'm
but
sure that we
then,
have some sense of like
but I think
neurons noticing light like coming
I
on.
think, but you also you need to have the morphology model of the light because, like as I said before, if you're going to like see the light and imagining it turning on, you have to start with a morphology model. Um, or if someone says, the light should turn on, well, you have to you're looking for the morphology of the light. It's otherwise you just have this, magical change in brightness. It's like, I,
Well, I
And then
think
there was
that
light.
maybe exists in the behavior model that you just want brightness to increase, and then
Yeah,
right.
for any kind
you
of
want
light.
illuminating. That's what you
So
want,
it seems,
illuminating.
one sort of sub goal, which might be more that we can even achieve next week, is I think you said this earlier, like just studying the one of these things, the switch. Like, okay, how do we exactly have a morphology model of the switch with two states that also connects to the behavioral model of the switch?
Yeah, that's where I would start.
Right.
Just morphology and behavior model and figure out how to connect them.
This is probably what you were saying earlier, and I didn't understand it. Right. Because that seems to be a pretty challenging problem all on its own. We haven't done that. In the end, it's going to be simple, but up front, it's like a little bit confusing. Once you do that, it's easy to do the same thing for the light bulb. I would imagine the light bulb is just a copy of the same thing we just did for the light switch. It's a morphology model with a behavior model. And then once you've got those, the causality connection is pretty straightforward. And then the next topic.
Yeah, go ahead.
Then the next thing would be how do you actually generate a behavior through some sort of subcortical projection.
Yeah, it seems like we had a pretty good idea about how we can learn the causality between the light switch and the light bulb. And
Right.
so yeah, now maybe taking a step back and going back to the very, very initial problem, maybe the reason why we even said we need to figure out behavior models first and go, okay, now we have behavior models. How can we connect it with the morphology model to affect a change in morphology?
Right. I don't think we've ever walked through that problem. At least I don't remember it. Like, oh, we've talked about it. We talked
Yeah,
about
we
it.
definitely talked about like how behavior and morphology models can be connected.
But
And
it's always been a little
stuff.
wavy, hand wavy, like,
Right.
oh, it's a child or whatever. I don't know. I mean,
yeah, I mean, we talked about how they could be connected for like assigning behavior to morphology, but we haven't, well, maybe we talked about it, but we haven't found any solution yet for how we can use the behavior model to figure out how to change the state of the morphology. Like assigning a behavior to
behavior model
morphology we
itself,
figured
right.
out, but not to, move through state space using the models.
Yeah, like I think, yeah, like you say, and I guess that's partly why I was focusing on here because it's kind of a recap. I feel like, yeah, we have a good sense of like linking up a bunch of different behavioral states.
like
I mean,
causality.
there's still some
Yeah.
open questions about that, but kind of, but yeah, like you say, like in the same sense that we use a morphology model to path integrate through that space, how we use the behavioral model itself
Yeah.
to inform.
Yeah, if you want,
how
I
to
can
act.
make a kind of intro visualization for the problem, at least how it's in my head, for the
Yeah,
beginning
that
of
sounds
next
good.
week.
I think that'd be good.
Okay.
That'd be good.
And yeah, hopefully
Right.
now after this recap, we have kind of all the puzzle pieces in place to
Right.
start
Right.
solving it now.
And right. And some of them were, some are more important than others, but it's good we went through them all. Figure that out. Right. It's so funny that such a simple thing is hard to think about. It's not like we're doing it wrong. We're doing it right. This is what's going on. It's just like, this is the story of, I guess, intelligence and brains, is like things that seem so simple are really very complex underneath. So
But then when we understand it, it often feels
right.
kind of
No, right,
simple
right. And I know
and almost obvious sometimes. And it's
that's
like,
right, exactly.
But I
It
think the
is
nice
that way.
thing is once we've solved the really simple problem, it should hopefully generalize to all of
Right,
the
right.
complex
I know,
problems
I
as
know.
well.
It's just funny. Here we are. Okay, just isolated light switch. Can we move it up and down?
it's also funny. Maybe this is what you were alluding to, Vivian, but like when I think like 2 years ago or even longer, almost 3 years ago, when we first talked about behaviors in Monty, we were like, can we just have a switch, just like a binary switch, and it just has to press it? And we were
Yeah.
thinking about how to like actually implement that in Monty before we'd spent too much time on like the theory side. Because I think we wanted like a candle to turn on or something like that. But
Yeah,
then we were
that was
like, would it be enough just to have a switch that goes from on to off?